March 18, 1944. 22,000 feet above Friedrichshafen, Germany. The temperature inside the nose of B-24J Liberator Liberty Bell sits at 18 degrees below zero. Second Lieutenant James McKnight presses his face against the plexiglass bombardier window, watching the patchwork German countryside slide beneath him through breaks in the cloud cover. His breath fogs the glass. Behind him, in the cramped fuselage, 9 other men ride in a machine that didn't exist in this form 3 years ago, a 4-engine heavy bomber that rolled off an assembly line in Michigan just 17 days earlier. The intercom crackles. Bombardier, pilot. 2 minutes to IP. McKnight acknowledges, fingers already reaching for the northern bombsight controls. Around Liberty Bell, 37 other B-24 Liberators from the 392nd Bomb Group hold formation, their olive drab and grey camouflage paint jobs catching the weak March sunlight. Each aircraft carries 8,000 pounds of high-explosive bombs in their bellies. Each aircraft costs $297,627. Each aircraft represents 360,000 man-hours of labor. And each aircraft came from the same impossible place. The flak starts at the initial point, black puffs of smoke erupting in the sky like dark flowers blooming in fast forward. A 88mm shell detonates 40 feet off the starboard wing. Shrapnel pings against Liberty Bell's aluminum skin. McKnight forces himself to focus on the target below, the Zahnradfabrik Friedrichshafen gear and transmission works. Critical to German tank production. Must be destroyed. Bomb bay doors open. The pilot's voice stays steady, professional, though everyone knows what open doors mean: more drag, slower speed, bigger target. Through the bomb site's optics, McKnight watches the factory complex crawl into the crosshairs. The math runs automatically in his head now, drilled into him through 50 practice runs over Texas rangeland. Altitude, airspeed, wind drift, trail angle. His right hand hovers over the release toggle. The entire formation depends on him. When he drops, 37 other bombardiers will follow, releasing nearly 300,000 pounds of ordnance in one concentrated strike. Behind him, in the waist gunner positions, Staff Sergeant Raymond Chen and Sergeant Michael Dutch Hollander scan the sky through their .50 caliber machine gun sights. At 22,000 feet, the German fighters would normally be up here by now, Me-109s and FW-190s tearing into the bomber stream with cannon fire. But today, the sky remains strangely quiet except for the flak. Steady, steady. McKnight breathes into the intercom. The factory slides into the bomb site's perfect center. His thumb presses down. Bombs away. 2.5 tons of high explosives tumble from Liberty Bell's spay. The aircraft lurches upward, suddenly 4,000 pounds lighter. McKnight watches the bombs fall in a graceful arc, then turns his attention to the lead aircraft's bombs, checking his timing, confirming the pattern. Good drop. The formation's bombs begin impacting across the target, orange fireballs erupting from factory buildings, black smoke rolling skyward. Pilot, bombardier. Bombs away, bay doors closing. Let's go home. But going home isn't simple. The 392nd still has to survive the return flight, 6 hours through hostile airspace, past more flak zones, potential fighter interception, fuel gauges slowly dropping. Mechanical failures happen. Engines quit. Hydraulics fail. Men get wounded, aircraft get shot to pieces, and crews have to nurse crippled bombers back to England or bail out over the Channel. Liberty Bell makes it. Not every B-24 does. As McKnight helps the pilot count the returning aircraft at their base in Wendling, England, he notes 2 empty spots in the formation. 2 aircraft that won't return. 20 men, possibly dead, possibly prisoners, possibly floating in the North Sea hoping for rescue. But here's the mathematics that keeps the 8th Air Force flying. Tomorrow, the 392nd Bomb Group will receive 2 brand new B-24 Liberators to replace the losses. Maybe 3. And the day after, 2 more. And the day after that, 2 more. A constant stream of bombers flowing across the Atlantic, replacing losses faster than the Luftwaffe can shoot them down. The Germans can't match this arithmetic. Every Heinkel bomber destroyed over Berlin, every Junkers Ju-88 shot down over Hamburg, those are losses the German aircraft industry strains to replace. Germany's factories operate on traditional manufacturing principles, skilled craftsmen building aircraft in small batches. A single German factory might produce 30 bombers per month. Perhaps 40, if pushed. But in America, in a building so large it has its own weather system, something revolutionary is happening. 18 months earlier. Willow Run, Michigan. Charles Emil Sorensen stands at the western end of the largest room in the world, watching workers install the first sections of assembly line track. Around him, the cavernous space echoes with the sound of riveting guns, welding torches, and shouted instructions. The building stretches ahead of him for more than half a mile, 3,200 feet of uninterrupted factory floor. At its widest point, it spans 1,280 feet. The ceiling vaults 60 feet overhead. Total floor space, 3.5 million square feet, or roughly 67 acres under one roof. This is Willow Run. Ford Motor Company's answer to the question, can you build a heavy bomber the way you build a car? Most people in the aircraft industry said no. They said it with absolute certainty, with condescension, with barely concealed contempt for the automobile manufacturer presuming to enter their specialized world. Building a B-24 Liberator isn't like stamping out Model TS, they said. Aircraft require precision. Tolerance is measured in thousandths of an inch. Complex systems, hydraulics, electrical, fuel, oxygen, all integrated with exacting standards. Each aircraft is essentially custom-built, they argued, requiring skilled craftsmen to hand-fit components and make countless small adjustments during assembly. Charles Sorensen disagrees. And at 61 years old, with 4 decades of manufacturing experience at Ford Motor Company, Sorensen has earned the right to his opinions. He's a big man, 6 feet tall with broad shoulders and large hands that still bear the calluses of his early days as a pattern maker. His Danish immigrant parents raised him to value precision and craftsmanship. His father was a wood carver who taught young Charles that any job worth doing was worth doing perfectly. Those lessons stayed with him through his rise at Ford, from pattern maker to Henry Ford's right-hand man, the genius who translated Ford's vision into reality on the factory floor. Sorensen designed the original Highland Park assembly line in 1913, the innovation that changed manufacturing forever. Before that line, Ford workers built cars at static stations, bringing parts to the vehicle. Sorensen reversed it, move the vehicle, keep the workers stationary. Each worker performs one specific task as the car flows past. Specialization. Repetition. Efficiency. The results spoke for themselves. Model T production time dropped from 12 hours to 93 minutes. Ford's prices dropped. Sales exploded. By 1927, Ford had built 15 million Model Ts. Sorensen's assembly line didn't just build cars, it built the modern manufacturing world. Now, in late 1942, Sorensen faces his greatest challenge. The U.S. Army Air Forces need bombers. Lots of bombers. Current production methods won't meet demand. Consolidated Aircraft San Diego plant builds B-24s at the rate of about 3 per day when running well. Goodbye aircraft industry standards. Pathetically inadequate for fighting a two-ocean war. Sorensen's solution, apply automobile assembly line principles to bomber production. Move the aircraft through stations. Break down construction into hundreds of small, repeatable tasks. Train workers to do each task perfectly. Let them practice until they achieve muscle memory. Then turn on the line and watch productivity soar. The aircraft industry experts called it impossible. They pointed out the differences. A B-24 contains 450,000 separate parts. It requires 1.25 million rivets. It's for Pratt & Whitney engines developed 4,800 combined horsepower. The aircraft weighs 65,000 pounds fully loaded. Wingspan, 110 feet. Length, 67 feet. This isn't a car, they insisted. You can't just bolt it together on a moving line. But Sorensen studied the B-24's blueprints with the same analytical intensity he'd applied to the Model T 30 years earlier. He saw a problem, yes, but a solvable problem. The B-24 consists of assemblies, wings, fuselage sections, tail assembly, engine nacelles. Each assembly contains sub-assemblies. Each sub-assembly contains components. Break it down far enough, and you're back to basic manufacturing operations: forming, cutting, riveting, welding, fitting. The key insight: parallel production streams. Don't try to build the entire aircraft on one line. Instead, create separate lines for major assemblies. Build wings on one line, fuselage sections on another, tail assemblies on a third. Then bring all these rivers of production together at a final assembly line where they merge into complete aircraft. Simple in concept, staggeringly complex in execution. Sorensen walks the factory floor now, yellow hard hat prominent on his head, making his daily inspection. He stops at Station 47, where workers are practicing the installation of wing skin panels. Each panel must align perfectly with the underlying structure, wing ribs, spars, and stringers that form the wing skeleton. The riveting pattern must be exact. Too few rivets and the panel might separate in flight, too many and you add unnecessary weight while potentially weakening the structure. How long for that panel? Sorensen asks the foreman. 22 minutes, Mr. Sorensen. Target: 18 minutes. Sorensen nods. They'll get there. The workers are still learning. In a month, they'll hit 18 minutes consistently. In 2 months, they might reach 16. The human element always surprises him. Give workers clear goals, proper tools, and systematic training, and they exceed expectations. He continues walking, making mental notes. The wing jigs at Station 52 need adjustment. He saw a slight misalignment that will cause problems downstream. The hydraulic line installation crew at Station 103 needs another training session with engineering. They're installing fittings backward, creating potential leak points. The electrical harness routing at Station 127 looks good, but they should add a secondary inspection point before the fuselage sections are mated. These details matter. Each small improvement multiplies across thousands of aircraft. Cut 30 seconds from one operation, and you've added 500 aircraft to annual production. Reduce defect rate by 2% at one station, and you eliminate thousands of hours of rework downstream. But the real challenge isn't the details. It's the scale. Willow Run scale defies comprehension. Sorensen knows this because he's watched visitors walk through the main entrance, take 10 steps, stop, and simply stare. The building swallows human perspective. Stand at one end, and the far wall becomes a hazy suggestion through the distance, an industrial haze. The ceiling trusses recede into infinity like the architecture of a cathedral designed by engineers instead of priests. The numbers tell part of the story. 3.5 million square feet of floor space requires 1.3 million square feet of roofing. The building consumed 300,000 cubic yards of concrete in its construction. Its heating system could warm a small city. When humidity rises inside, clouds form near the ceiling, literal clouds that sometimes produce rain on the factory floor. Workers on the final assembly line occasionally need umbrellas. But numbers don't capture the human challenge. Sorensen needs 42,000 workers to run Willow Run at full production. 42,000 people, most of whom have never built anything more complex than a garage shelf, who must learn to construct the most technologically sophisticated bomber in America's arsenal. It's December 1942, and Sorensen faces a crisis. Willow Run has been operating for 5 months. Production stands at 14 aircraft per month. Pathetic. Unacceptable. The Army Air Forces wanted 150 per month by now. Congress is asking questions. Newspaper editorial writers are sharpening their knives. Will it run? They're calling the plant. A clever play on words that makes Sorensen's jaw tighten every time he hears it. The problems cascade like dominoes. Workforce turnover approaches 60% annually. Workers arrive, get overwhelmed by the complexity, and quit. The housing shortage around Ypsilanti means workers commute from Detroit, spending 3 hours daily in transit, arriving exhausted. Parts shortages halt production, suppliers can't meet delivery schedules. Engineering changes from Consolidated Aircraft's San Diego headquarters arrive weekly, forcing line modifications. And the workers they do retain are making mistakes, small errors that compound into major problems. Sorensen stands in his office overlooking the factory floor at 2 a.m. on December 19th. He hasn't slept properly in weeks. Below him, the night shift struggles with fuselage section 42 to 8173, trying to determine why the tail section won't mate properly with the rear fuselage. They've been working on it for 6 hours. 6 hours for an operation that should take 45 minutes. This is the price of innovation. Everyone wants the results of the assembly line, the speed, the efficiency, the impossible production numbers. Nobody wants to endure the painful learning curve. Meade Bricker enters the office without knocking. Bricker serves as Sorensen's production superintendent, a 34-year-old engineer who came up through Ford's tractor division. He's got the hollow-eyed look of a man running on coffee and determination. Section 8173's tail alignment problem, Bricker says. The San Diego drawings show the tail mount bolt holes at 47.3 inches on center. Our jigs are set for 47.5 inches. Who's wrong? We are. San Diego sent a revision 3 weeks ago. It got lost in processing. Sorensen closes his eyes briefly. This happens too often. Consolidated Aircraft in San Diego designed the B-24. They're still designing it. Actually, the aircraft evolves constantly as combat experience reveals improvements. Each change requires new drawings, new specifications, new jig settings. The system for distributing these changes resembles a game of telephone played across 2,000 miles with thousands of participants. Pull the engineering team off sleep rotation, Sorensen says. I want every drawing checked against San Diego's master specs. Everything. Wings, fuselage, tail, engine mounts, everything. Find every discrepancy. That's 30,000 drawings, Mr. Sorensen. Then they'd better start now. Bricker nods and disappears. Sorensen returns to the window. On the factory floor, workers are beginning to remove the misaligned tail section from fuselage 8173. It'll be 6 more hours before they can restart installation. 1 aircraft, 1 day behind schedule. Multiply that by every problem on the line, and you see why production numbers remain abysmal. But Sorensen didn't get where he is by accepting failure. He attacks the problems systematically, the way he'd debug a balky transmission line. January 1943. The workforce problem requires multiple solutions. First, stabilize housing. Sorensen pushes Henry Ford to build dormitories near the plant. Ford reluctantly agrees, and by March, 2,500 units of temporary housing rise on the farmland surrounding Willow Run. Not luxury accommodations, cinder block buildings with communal bathrooms, but close enough that workers can walk to their shifts. Second, improve training. Sorensen raids Ford's other plants for their best instructors, creating a training center that processes 200 new workers per week. The program runs 8 weeks, longer than any automotive training, covering everything from reading blueprints to proper riveting technique. Each worker receives a handbook specific to their station. Each station gets photo boards showing correct assembly procedures. The riveting stations get special attention. A B-24 requires 1.25 million rivets, and each rivet must be installed perfectly. Too loose, and it won't hold under stress. Too tight, and you deform the aluminum, creating stress points. Wrong angle, and you compromise the aircraft's aerodynamics. Sorensen establishes quality control inspectors who check every 10th rivet at each station. Aircraft that fail inspection go back for rework, and the responsible worker gets retraining. Martha Sorensen, no relation to Charles, learns riveting in February 1943. She's 23, from a farm outside Ann Arbor, and she's never held a rivet gun before arriving at Willow Run. Her trainer, a gruff 40-year-old automotive veteran named Pete Kowalski, spends the first week teaching her just one thing: how to identify a good rivet from a bad one. "Look here," Kowalski says, holding up a practice panel. "This rivet sits flush. The shop head, that's the part you make with the gun, it's round, centered over the hole, no cracks. Good rivet." He points to the next one. "This one? Shop head's oval. That means the gun wasn't square to the work. Stress concentrator. Fail." Martha learns to feel it in her hands, the resistance when the gun hits the rivet, the vibration that tells her whether the rivet's forming properly. After 2 weeks, she can install 20 rivets per minute with a 98% first-time success rate. After 4 weeks, she's training new workers. By March 1943, Willow Run employs 15,000 women. They work every job men do: riveting, welding, electrical installation, hydraulics, final assembly. The poster of Rosie the Riveter shows a muscular woman flexing her bicep under the caption, "We can do it." The model was a Willow Run worker named Naomi Parker Fraley, photographed operating a lathe in Building CR5. Third challenge: part supply. A B-24 contains 450,000 parts from 1,500 different suppliers scattered across America. Pratt & Whitney engines from Connecticut. Propellers from Ohio. Instruments from New York. Tires from Ohio. Guns from Connecticut. Aluminum from Tennessee. Each supplier must deliver parts on a precise schedule: too early, and Willow Run's limited storage space overflows; too late, and the line stops. Sorenson implements a system borrowed from Highland Park: scheduled delivery. Each supplier gets a delivery window measured in hours, not days. Train cars and trucks arrive at Willow Run's rail yards and loading docks at predetermined times. Parts move directly from transport to the appropriate production station. Inventory never sits more than 48 hours. When suppliers miss deadlines, Sorensen sends Ford expediters to their plants, men with authority to solve problems on the spot. A gear manufacturer in Pennsylvania falls behind schedule because they can't get raw steel. The Ford expediter identifies an alternative supplier, arranges steel delivery, and has the gear plant back on schedule within 72 hours. The engineering changes problem proves harder. Consolidated Aircraft keeps modifying the B-24 design. Combat experience over Europe reveals vulnerabilities: insufficient armor, weak defensive armament, fuel systems prone to fire. Each fix requires design changes. The B-24D model gives way to the B-24E, then the B-24G, each incorporating improvements. But Willow Run can't change on a whim. The assembly line has 500 stations. Each station has tools, jigs, fixtures designed for specific operations. An engineering change might affect 20 stations, requiring new jigs, retraining workers, adjusting the line balance. A single change can cost a week of production. Sorensen's solution: standardization. He negotiates with Consolidated and the Army Air Forces. Willow Run will build one model at a time, incorporating all approved changes at once during planned transitions. No more weekly modifications. Instead, they'll produce B-24E bombers until engineering completes all B-24G changes, then shut down for 3 days to reconfigure the line, then produce B-24GS. The Army resists. They want changes implemented immediately. But Sorensen shows them the math: continuous small changes reduce production by 30%. Planned transitions reduce production by only 5%. The Army agrees. March 1943. Production reaches 31 aircraft. Still far below target, but improving. The learning curve shows progress. Workers are getting faster. Quality defects decline. The parts pipeline stabilizes. Sorensen can feel the system beginning to function as designed. But he needs more. Much more. He studies the bottlenecks. Final assembly takes the longest, where all the major sub-assemblies come together. Wings mate to fuselage. Engines install on wing mounts. Tail section attaches. Fuel systems connect. Hydraulics, electrical, oxygen, intercoms, hundreds of systems integrate into one functional aircraft. Currently, final assembly takes 19 days per aircraft. Sorensen wants it down to 5. He breaks down every operation. Wing attachment requires 12 hours, can't reduce that much, it's precision work. But engine installation takes 8 hours per engine. 32 hours total. That seems excessive. He studies the operation. The problem, engines arrive partially disassembled. Workers must install accessories, generators, carburetors, ignition systems, before mounting engines on the wings. For engines, 8 hours each. But what if engines arrived fully assembled? Sorensen creates a sub-assembly line dedicated to engine preparation. Pratt & Whitney engines arrive at Station E01. Workers install all accessories at dedicated benches with specialized tools. By Station E17, engines are complete, ready to bolt onto wing mounts. Installation time drops from 8 hours to 90 minutes per engine. He applies the same analysis to every operation. Fuel tank installation. Control cable routing. Oxygen system pressure testing. Radio installation. Each operation gets studied, broken down, optimized. The instrument panel installation particularly frustrates him. It takes 6 hours, inserting dozens of instruments into the panel, connecting wiring behind it, testing each instrument. 6 hours for work that should take 2. The solution comes from an unexpected source. Eleanor Kowalski, Pete's daughter, works in the instrument section. She suggests pre-wiring the instrument panel. Install all instruments on a bench, connect all wiring, test everything, then install the complete panel as one unit. Sorensen authorizes a test. Installation time drops to 95 minutes. He promotes Eleanor to section supervisor and gives her a $500 war bond. By April 1943, Willow Run produces 53 aircraft. May, 75. June, 91. The assembly line is starting to sing. But Sorensen wants it to roar. He stands at the final assembly station, watching a B-24 roll off the line. The aircraft gleams under the factory lights, aluminum skin catching reflections from welding torches, red primer visible through inspection panels not yet closed. In 24 hours, this bomber will fly to Modification Center where they'll install guns, armor, and secret equipment. Then to England. Then to Germany. He calculates 91 aircraft in June means roughly 3 per day. Each aircraft requires 30 workers on final assembly, working in shifts. The line runs 24 hours, 3 shifts. If he can optimize workflow, reduce the time each aircraft spends in each final assembly station. He gets out his slide rule. The calculations are complex but the logic is simple. The final assembly line has 42 stations. Average time per station, 8 hours. If he can reduce that to 6 hours, just 2 hours per station, each aircraft moves through the system in 11 days instead of 14. That's a 20% increase in throughput without adding workers or floor space. Meade Bricker finds him 90 minutes later, still calculating. You're going to hit them with a new efficiency program, aren't you? Bricker says. We're going to break our own records, Sorensen replies. Then we're going to break them again. The workers are already exhausted. Then we'll train more workers. Build more jigs. Add more quality inspectors so they catch problems earlier. Install better lighting so they work faster at night. Improve the tool management system so they waste less time hunting for wrenches. When do you want to start? Yesterday. Bricker grins. He's heard this before. I'll brief the foreman. Sorensen returns to his calculations. Somewhere over Germany, B-24 crews are fighting for their lives. Every bomber he builds might save 10 American lives. Might help win the war. Might end the fighting one day sooner. He's not building bombers. He's building hope, manufactured at industrial scale. July 12, 1943. 6:47 a.m. Willow Run, Station FA-27. Robert Janssen fits the starboard wing root fairing onto B-24J serial number 42 to 50,786, his hands moving with practiced precision. The fairing, a streamlined aluminum panel that covers the junction where wing meets fuselage, requires exact positioning. 3 mm off, and it won't seal properly, creating drag that costs the aircraft 5 miles per hour. In combat, 5 miles per hour means the difference between evading a fighter and getting shot down. Janssen knows this. Every worker at Willow Run knows this. Sorensen made sure of it. The morning shift started 17 minutes ago. Around Janssen, 14,000 workers move through their stations in choreographed precision. The factory floor hums with controlled chaos, pneumatic rivet guns chattering like mechanical insects, cranes swinging major assemblies overhead, electric motors whining as they drive conveyor systems. The smell of hot aluminum, cutting oil, and ozone from arc welders fills the air. Janssen Station allows him 12 minutes for the fairing installation. He'll finish in 10. He's been doing this job since March, for months, over 200 aircraft. His hands know the work better than his conscious mind. Align the panel. Check the mating surface for debris. Apply sealant to the gasket. Position the fairing. Insert 6 Dzus fasteners. Torque each to specification. Visual inspection. Sign off the work ticket. Done. He moves to the next aircraft on the line, 42 to 50,787, already positioned at his station. 12 minutes per aircraft. 5 aircraft per hour. 40 aircraft per 8-hour shift. At the end of the line, one completed B-24 Liberator emerges every 73 minutes. But Sorensen wants 63. The production curve climbed through July. 98 aircraft that month. Then August, 125. September, 148. October, 175. Each month sets a new record. Each month, Sorensen pushes harder. The breakthrough comes from obsessive attention to cycle time, the minutes each aircraft spends at each station. Sorensen and his team analyze every operation with stopwatches and clipboards, creating detailed time-motion studies that would have impressed Frederick Taylor himself. Station FA-19 hydraulic line connection takes 14 minutes. Can it be reduced? Study reveals workers waste 3 minutes retrieving fittings from supply bins 30 feet away. Solution: mobile tool carts at each station, pre-stocked with required parts. Time drops to 11 minutes. Station FAR-33, electrical harness routing takes 22 minutes. Analysis shows workers spend 7 minutes consulting wiring diagrams. Solution: overhead projection systems that display the correct routing diagram for each aircraft variant automatically. Time drops to 15 minutes. Station FAR-41, cockpit instrument testing takes 18 minutes. Workers test each instrument individually, waiting for each to warm up. Solution: parallel testing equipment that checks 6 instruments simultaneously. Time drops to 12 minutes. Multiply these savings across 500 stations, and hours vanish from the production cycle. But the real breakthrough comes from changing how work flows through the factory. Sorensen realizes final assembly is still the bottleneck. Wings arrive from Wing Building 1. Fuselage sections arrive from Fuselage Assembly Building. Tail sections from Empennage Building. These major assemblies converge at final assembly, where they wait in queue. The wait kills productivity. An aircraft sitting idle is money burning. Sorensen implements just-in-time delivery for major assemblies. Wings complete at Wing Building 1 at 9:17 a.m. They arrive at final assembly station FAR-1 at 9:31 a.m., exactly when needed, not 1 minute sooner. Fuselage sections complete at 2:43 p.m., arrive at their station at 2:58 p.m. This requires phenomenal coordination. Every upstream process must hit its schedule within a 15-minute window. Miss the window, and the final assembly line stops. Stop the line, and Sorensen will personally find out why. The supervisors learn quickly. James Brightwell runs Wing Building 1. He's a former Ford automotive supervisor who came to Willow Run in November 1942. His job is to deliver 12 completed wing sets per shift, 24 wings total, to final assembly. Each wing set must arrive within its scheduled window. Brightwell treats these schedules like religious obligations. He posts the delivery times at every station. He has runners circulating every 30 minutes, checking progress. If Station W17 falls behind, Brightwell reassigns workers from stations running ahead. If a tool breaks at Station WE32, Brightwell has backup tools delivered within 5 minutes. On September 22, 1943, Wing Building 1 delivers 12 wing sets on schedule for the 37th consecutive shift. Brightwell's workers earn a bonus. More importantly, they earn respect. In a factory this large, reputation matters. Final assembly knows Wing Building 1 will deliver. They plan around it. The same discipline spreads through every building. Fuselage assembly. Empennage. Engine preparation. Sub-assembly shops. A massive industrial organism learning to move as one. November 8, 1943. 2:33 p.m. Final assembly, Station FAF42. Mary Catherine Rodriguez watches B-24J serial number 42 to 51,234 roll off the end of the final assembly line. This is the last station, the moment where a collection of parts officially becomes an aircraft. Rodriguez's job is final inspection. She has 45 minutes to check everything before the aircraft moves to the run-up area for engine testing. She climbs the ladder to the flight deck, inspection checklist in hand. The cockpit still smells of new aluminum, hydraulic fluid, and electrical insulation. Overhead, the bombardier's compartment gleams with fresh plexiglass. Behind her, the bomb bay doors wait open, revealing the empty bay where 8,000 pounds of ordnance will soon hang. Rodriguez checks the pilot's controls. Control yokes move freely. Rudder pedals respond. Throttle quadrant operates smoothly. She verifies the instrument panel, 37 instruments, every one secured, every connection tight. The radio equipment receives power. The autopilot responds to input. The oxygen system holds pressure. She descends to the bomb bay, checking the catwalk, the narrow beam that crew members traverse to reach the rear of the aircraft. One bad rivet here, one weak support, and a crewman might fall through at 20,000 feet. The catwalk is solid. She checks the bomb shackles, the releases that drop bombs on target. Each one operates correctly. 45 minutes later, she signs off aircraft 42 to 51,234 as airworthy. The bomber taxis to the run-up area, where test pilots will spend 2 hours verifying every system under power. Then to the modification center for military equipment installation. Then to Europe. Rodriguez climbs down from the aircraft and looks back at the assembly line. Another B-24 is already positioned at her station, waiting for inspection. She's processed 5 aircraft today. Tomorrow she'll process 5 more. By November 1943, Willow Run produces 189 aircraft per month. That's 6.3 per day. 1 every 3 hours and 48 minutes. Sorensen stands in his office, looking at the production charts. The curve climbs steeply now. But it's not enough. Not yet. December 1943. Winter settles over Michigan. Snow drifts accumulate around Willow Run's perimeter. Inside, the massive heating system struggles to maintain temperature. Workers on the final assembly line wear coats while they work. Their breath creates fog that mingles with the industrial haze. But production doesn't stop. Can't stop. In Europe, bomber crews are dying in burning aircraft, freezing in the North Atlantic, starving in German prison camps. Every aircraft matters. Every hour matters. Sorensen implements the final optimizations. The learning curve has plateaued at most stations, workers have achieved maximum efficiency through practice. Further improvements require system changes. He adds third-shift supervisors at bottleneck stations. He installs better lighting. The night shift was working too slowly because they couldn't see properly. He creates a rapid response maintenance team that fixes broken equipment within minutes instead of hours. He establishes a quality prediction system. Inspectors identify which stations produce the most defects and increase oversight there before problems cascade downstream. The paint shop becomes a focus. Applying camouflage paint, olive drab over neutral gray, takes 6 hours. Sorensen investigates. The painters are using brushes and rollers. He installs spray equipment. Paint time drops to 90 minutes. The electrical systems testing station takes too long. Sorensen discovers that the testing equipment itself is unreliable. False positives force workers to retest circuits that are actually functional. He brings in electrical engineers from Ford's automotive division. They design better testing equipment. False positive rate drops from 12% to 2%. By January 1944, production hits 225 aircraft per month. One every 3 hours and 12 minutes. But the factory can go faster. Sorensen knows it. He can feel the potential in the system, like a race car that hasn't quite reached its maximum RPM. The final barrier is psychological. Workers believe 3 hours per aircraft is close to theoretical maximum. They're working hard, efficiency is high, quality is good. What more can anyone ask? Sorensen asks for more. February 15, 1944. 11:22 a.m. Sorensen gathers his supervisors in the main conference room. 37 men and 3 women, the people who make Willow Run function. They look exhausted. Most have been working 60-hour weeks for 18 months. Gentlemen, ladies, Sorensen begins, we're producing 7.5 aircraft per day. That's excellent. You should be proud. But I'm going to ask you to go faster. The room stays silent. They've heard this before. We're going to produce 1 aircraft every 63 minutes, Sorensen continues. That's 11 points for aircraft per day. 342 per month. James Brightwell from Wing Building speaks first. Mr. Sorensen, with respect, we're already at capacity. Workers are optimized. Equipment runs continuously. I don't see where we find another 4 aircraft per day. We find it in the gaps, Sorensen replies. He walks to the chalkboard and draws the production timeline. An aircraft spends 16 hours on final assembly. But it only receives active work for 11 of those hours. 5 hours are wasted, waiting for parts, waiting for tools, waiting for inspectors, waiting for the previous operation to complete. He taps the board. We eliminate the waiting. Every station has parts pre-staged. Every station has backup tools ready. Every station has an inspector assigned, not shared. We create buffer zones, small inventory positions where completed assemblies wait so the line never stops for upstream delays. Mead Bricker nods slowly. You want to decouple the stations. Make each one independent. Exactly. If wing building has a problem, final assembly keeps running from buffer stock. We fix the problem, replenish the buffer, maintain flow. That requires inventory space, someone objects. We have 3.5 million square feet, Sorensen counters. We'll use it. Over the next 6 weeks, Willow Run transforms again. Buffer zones appear throughout the factory, designated areas where completed assemblies wait. Wing sets stack in specially designed racks near final assembly. Fuselage sections line up in carefully managed queues. Engine nacelles sit on mobile stands, ready to roll to their installation stations. The system requires careful management. Too much buffer inventory and you waste space and money. Too little and stations run dry. Sorensen establishes inventory controllers who monitor buffer levels constantly, adjusting upstream production rates to maintain optimal flow. The parts delivery system expands. Sorensen hires 200 additional material handlers whose only job is moving parts to stations. They operate on precise schedules, delivering specific parts to specific stations at specific times. Station FAR-19 needs 47 hydraulic fittings delivered at 9:15 a.m., 1:45 p.m., and 10:30 p.m. The material handlers deliver exactly that. Never early, that creates clutter. Never late, that stops work. Tool management becomes systematized. Every station gets duplicate tool sets. Primary tools in use, backup tools in storage lockers 30 feet away. When a tool breaks, workers grab the backup immediately, hang a red tag on the broken tool, and continue working. Maintenance collects broken tools on regular rounds, repairs or replaces them, and returns them to storage. The inspection system changes. Instead of roving inspectors who check multiple stations, each critical station gets a dedicated inspector. The inspector works alongside the production workers, checking work continuously instead of in batches. Problems get caught immediately, not hours later after the aircraft has moved downstream. Quality improves. Speed increases. The line begins to flow. April 1944. At 3:17 p.m. on April 24, 1944, B-24J serial number 42 to 52,436 rolls off the final assembly line at Willow Run. Nothing distinguishes this aircraft from the hundreds that preceded it. Same olive drab and neutral grey camouflage. Same for Pratt & Whitney engines. Same defensive armament points awaiting guns at the modification center. But the production clock tells a different story. Aircraft 42 to 52,436 spent exactly 63 minutes on final assembly, from the moment its wings mated to the fuselage until Mary Catherine Rodriguez signed the final inspection sheet. 63 minutes. 1 hour and 3 minutes. From major assemblies to complete bomber. Sorensen isn't present when it happens, he's in Detroit, meeting with Army Air Forces procurement officers about 1945 production quotas. But Meade Bricker is there. He watches the clock, watches the aircraft roll out, and allows himself a rare smile. They've done it. The impossible thing. The thing the aircraft industry said couldn't be done. Production stabilizes at this new rate. May 1944, 343 aircraft. June, 356. July, 362. Month after month, one B-24 Liberator emerges from Willow Run every 63 minutes during production hours. The math becomes staggering. Ford's Willow Run produces more aircraft than the entire German aviation industry. More bombers than all other American B-24 plants combined. The factory operates 24 hours daily, 7 days weekly. The line never stops except for planned maintenance. Bombers flow like automobiles, an aluminum river of destruction pointed at the Third Reich. In England, the 8th Air Force's strength grows dramatically. Groups that flew with 18 aircraft per mission in 1943 now fly with 36. Losses still happen, flak still kills, fighters still attack, mechanical failures still force crews to bail out over the North Sea. But replacements arrive faster than losses accumulate. The math shifts inexorably in America's favor. German fighter pilots report the phenomenon with growing dread. In 1943, destroying 30 B-24s in a month represented a significant victory. By mid-1944, Willow Run replaces 30 B-24s every 2 days. The Luftwaffe can't match this arithmetic. Germany's aircraft factories operate with skilled craftsmen building bombers in small batches. They produce quality aircraft, but nowhere near the quantity emerging from Michigan. Sorensen finally visits the line on May 3, 1944. He walks the final assembly floor at midnight, watching the night shift work. Aircraft move through stations in steady progression. Workers execute their tasks with casual expertise. Inspectors check quality. Material handlers deliver parts. The system functions. At station FAR-42, he watches another B-24 rollout. The bomber gleams under the factory lights, ready for test flight. Mr. Sorensen. A young worker approaches, can't be more than 20. I wanted to thank you, sir. For what? My brother flies B-24s. 458th Bomb Group, England. He wrote me last month. Said his aircraft came from Willow Run, he could tell from the serial number. Said it's a good ship. Tight construction, no problems. Might have saved his life in a rough mission. The worker extends his hand. Thank you for making sure we do this right. Sorensen shakes his hand. Thank you for building them right. The worker returns to his station. Sorensen continues walking. 61 years old now, tired in his bones, but satisfied. This is his last great achievement, proof that American manufacturing can overcome any challenge through innovation, determination, and systematic thinking. The bombers keep rolling. One every 63 minutes. An iron river flowing to Europe, to the Pacific, to every theater where America fights. And somewhere in that river, one young pilot will fly a bomber built by his brother, never knowing the connection, only knowing that his aircraft brings him home safely. August 6, 1944. 31,000 feet above Magdeburg, Germany. First Lieutenant Thomas Garrett holds B-24J Hellsbell steady in formation, his eyes scanning the sky for fighters. Around him, 42 other Liberators from the 467th Bomb Group maintain their combat box, a defensive formation designed to maximize overlapping fields of fire from the .50 caliber machine guns bristling from each aircraft. They're 10 minutes from the target, the Brabag synthetic oil plant, one of Germany's critical fuel production facilities. Hellsbell is 11 weeks old. She rolled off the Willow Run line on May 23, 1944, serial number 44 to 40,457. She crossed the Atlantic in early June, joined the 467th at Rackheath, England, and flew her first combat mission on June 17. Today is her 28th mission. The law of averages says most B-24s don't survive 35 missions. But Garrett and his crew take care of their ship, and their ship takes care of them. The flak starts at 10:47 a.m., black bursts of 88mm shells exploding across the sky. A nearby B-24 from the 788th Squadron takes a direct hit in the bomb bay. The aircraft disintegrates in a massive fireball, scattering debris across 3 square miles. No parachutes. 10 men gone in an instant. But the formation doesn't break. Can't break. The mission requires precision. Garrett flies straight and level despite the flak, despite the fear, despite knowing that every second over the target increases the odds of dying in a burning aircraft. Bombardier, pilot. 30 seconds. The bomb bay doors open. 2.5 tons of high explosives arm themselves, waiting for the bombardier's release. Bombs away. Hellsbell leaps upward as the bombs fall away. Garrett banks left, following the formation through evasive maneuvers designed to throw off flak gunners' aim. Behind them, the Brabag plant erupts in flames, multiple bomb strikes across the critical production facilities. Thick black smoke rolls skyward. The formation turns for home. 6 hours of flying remain. 6 hours of nursing engines, monitoring fuel, watching for fighters, hoping the aircraft holds together. Hellsbell makes it back. She always does. Garrett sets her down on Rackheath's runway at 4:33 p.m. The ground crew swarms the aircraft, checking for damage, refueling, rearming. By dawn tomorrow, she'll be ready for another mission. This is what Willow Run built. Not just bombers, the means for America to sustain an air campaign that would have been impossible using traditional aircraft manufacturing. The 8th Air Force can now launch 1,000-plane raids and absorb 50-plane losses because Willow Run and other factories replace those losses within days. The arithmetic that once favored Germany's defenders now crushes them. Willow Run, August 1944. Production peaks this month at 432 aircraft, 14 per day, one every 63 minutes during production hours. The factory operates with mechanical precision. The workforce stabilizes at 42,000, turnover drops below 15% as workers master their jobs and take pride in their contribution. Housing improves. Transportation improves. Training improves. Everything that Sorensen fought to establish now functions as designed. The numbers tell the story. From January 1943 to August 1944, Willow Run produces 6,791 B-24 Liberators. That's more heavy bombers than the entire Luftwaffe possesses at this point in the war. More than all Japanese aircraft production combined during the same period. One factory in Michigan outproduces the aviation industries of two major military powers. But the achievement extends beyond numbers. Willow Run proves that complex military equipment can be mass-produced without sacrificing quality. Early concerns about assembly line aircraft being inferior to handcrafted planes prove unfounded. Combat reports consistently rate Willow Run B-24s as equal or superior to those from other manufacturers. The aircraft perform well, hold together under combat stress, and bring crews home. Charles Sorensen receives the Army Navy EAD Award for Excellence in Production, a pennant that flies above Willow Run's main entrance. He accepts the award on behalf of the workers, not himself. In his brief speech, he tells the assembled crowd, "You built these aircraft. You made the impossible possible. When the history of this war is written, your contribution will be remembered as one of the great industrial achievements of our time." He believes it. The workers believe it. And as B-24s continue rolling off the line at 63-minute intervals, the proof becomes undeniable. October 1944. The air war over Europe shifts. Allied fighters now dominate the skies, P-51 Mustangs escort bomber formations all the way to Berlin and back. Luftwaffe fighter strength collapses under the weight of unsustainable losses. German pilots increasingly refuse to engage heavily escorted bomber formations. The aerial bloodbaths of 1943, when 30 or 40 bombers might be shot down in a single mission, become rare. But the bombing continues. The 8th Air Force and RAF Bomber Command drop thousands of tons of ordnance daily on German industrial targets, transportation networks, and oil facilities. Every mission requires bombers. Willow Run supplies them. On October 14, 1944, exactly 1 year after the disastrous second Schweinfurt raid that cost the 8th Air Force 60 B-17s, a 1,000-plane raid strikes Cologne. Only 2 bombers are lost. The math has changed. German flak remains deadly, but it cannot stop the aerial avalanche. At Willow Run, production continues at full capacity. But rumors circulate. The war in Europe won't last forever. Germany's military collapses on all fronts. Soviet armies push from the east. Allied armies advance from France. Italy has already surrendered. Japan fights on in the Pacific, but the outcome seems inevitable. What happens to Willow Run when the war ends? Sorensen knows the answer. He's been preparing for it since mid-1944. B-24 production will end. The Army Air Forces already projects reduced bomber requirements for 1945. The factory will shut down, tens of thousands of workers will lose their jobs, and the greatest assembly line ever created will fall silent. But not yet. Not while men are still fighting. Not while bombers are still needed. January 1945. In the winter cold, production continues. But the pace slows slightly, not from inefficiency, but from planned reduction. The Army Air Forces cuts orders. They have enough bombers now. The strategic bombing campaign achieved its objectives. Germany's oil production collapsed. Transportation networks lie in ruins. Industrial capacity decimated. Willow Run produces 362 aircraft in January, 341 in February, 289 in March. The decline is controlled, managed. Sorensen begins laying off workers in phases, starting with those hired most recently. He works with the United Auto Workers Union to ensure fair treatment, severance pay, and assistance finding new employment. It hurts. These workers built something extraordinary. They deserve better than unemployment. But Sorensen can't change the reality: the war is ending, and with it, the need for bombers. On April 12, 1945, President Roosevelt dies. The nation mourns. At Willow Run, workers observe a moment of silence at noon. Then they return to building bombers. The work continues. On May 7, 1945, Germany surrenders. In Europe, the war ends. Celebrations erupt across America. At Willow Run, workers cheer, embrace, cry with relief. Their brothers, sons, husbands, and sweethearts will come home. The bombers they built helped win the war. But victory brings consequences. Within days, the Army Air Forces cancels remaining B-24 orders. Willow Run's production line will shut down completely by June 28, 1945. June 28, 1945. 3:47 p.m. B-24M serial number 44 to 51,228 rolls off the Willow Run final assembly line. This is the last one. The 8,685th bomber produced at this factory. The end of the line. Charles Sorensen stands at station FA-42, watching the final aircraft emerge. Around him, a skeleton crew of workers, most have already been laid off, observe the moment. The massive factory, once echoing with the sound of 42,000 workers building an aluminum river of destruction, now feels hollow. Vast empty spaces where wing assemblies once waited. Silent stations where workers once riveted fuselage sections. Darkened overhead cranes that once swung engines into position. Mary Catherine Rodriguez performs the final inspection on 44 to 51,228. She's been here since November 1943. She's inspected over 2,000 aircraft. Every one met her standards. This last one will too. She signs the inspection sheet at 4:33 p.m. B-24M 44 to 51,228 is airworthy. The aircraft taxis to the run-up area for engine testing. Tomorrow it will fly to storage. The war in the Pacific continues, but the need for new B-24s has ended. This bomber will likely never see combat. It will sit in the Arizona desert with hundreds of others, waiting for a mission that never comes. But that doesn't diminish what it represents. Sorensen gathers the remaining workers. About 200 people, supervisors, foremen, key technical staff, and a few production workers who volunteered to stay until the end. You built 8,685 heavy bombers, Sorensen tells them. More than any other single factory in history. You produced one complete aircraft every 63 minutes at peak production. You proved that complex machines can be mass-produced without sacrificing quality. You helped win the war. He pauses, looking at the faces before him. Young and old. Men and women. People from farms and cities, from Michigan and across America, who came together to accomplish the impossible. Thank you, Sorensen says simply. You changed the world. The workers applaud, not for him, but for themselves. For what they achieved together. For the bombers they built. For the lives they saved. For their small part in defeating fascism and ending the most destructive war in human history. The gathering disperses. Workers collect their tools, clean out their lockers, say goodbye to colleagues they may never see again. By 6 p.m., Willow Run stands nearly empty. The production line sits silent. The lights dim. The massive factory that once pulsed with life falls dormant. Epilogue. Charles Sorensen retires from Ford Motor Company in 1944, after 40 years of service. He's 63 years old, tired but satisfied. Willow Run represents his final masterpiece, the culmination of a career spent perfecting mass production. He lives another 24 years, dying in 1968 at age 87. He never speaks much about Willow Run. When asked, he deflects credit to the workers, the engineers, the countless people who made the system function. But those who worked with him know the truth: without Sorensen's vision, determination, and expertise, Willow Run never would have succeeded. The factory itself survives the war, briefly producing automobiles before closing in the 1950s. For decades it sits abandoned, a massive monument to industrial capability. Parts are demolished. Nature reclaims sections. Preservationists fight to save the building, but economics work against them. In 2013, most of Willow Run is demolished. A small section survives as a museum, the Yankee Air Museum, preserving a fragment of the world's most productive bomber factory. The B-24 Liberators built at Willow Run scatter across the globe. Some fight in Europe until Germany surrenders. Others deploy to the Pacific for the final campaigns against Japan. After the war, most are scrapped, aluminum melted down for peacetime purposes. A few survive in museums, preserved as examples of America's industrial might. Hell's Bell, First Lieutenant Thomas Garrett's bomber, completes 39 missions before being retired in October 1944. She returns to the United States, flies in war bond tours, then goes to storage in Arizona. Eventually scrapped in 1947. Garrett survives the war, returns to Iowa, and lives to age 79. He never forgets his B-24, the ship that brought him home safely 28 times. The workers disperse. Martha Sorensen returns to her farm outside Ann Arbor, marries, raises 3 children, and lives to age 92. She never tells her grandchildren about her war work until they discover old photographs in her attic. Robert Janssen moves to California, works in aerospace during the Cold War, and helps build components for Apollo spacecraft. Mary Catherine Rodriguez becomes a quality control inspector for Ford's automotive division, retiring in 1983 after 40 years in manufacturing. They built bombers. They changed history. They proved that American democracy, when challenged, could mobilize industrial power on a scale never before seen. March 18, 1944. 22,000 feet above Friedrichshafen, Germany. Back to where we began. Second Lieutenant James McKnight in the nose of Liberty Bell, watching bombs fall on the German factory below. The aircraft that carries him, built at Willow Run in 63 minutes of final assembly time, performs flawlessly. Every rivet holds. Every system functions. The bomber takes hits from flak, absorbs the damage, and keeps flying. McKnight doesn't know about Charles Sorensen. He's never heard of Willow Run. He doesn't understand the revolutionary manufacturing techniques that made his aircraft possible. He just knows that his bomber works, that it brings him home, that somewhere in America workers are building more bombers to replace the ones being shot down. That's enough. That's everything. The mathematics of war are brutal but simple. You must be able to replace losses. You must sustain operations through attrition. You must build faster than the enemy can destroy. Willow Run proved America could do all three. One factory manager applied automobile assembly techniques to bomber production. One massive building housed the world's longest assembly line. At peak production, the facility completed a 4-engine B-24 Liberator every 63 minutes. 8,685 bombers total, demonstrating that American industry could build complex aircraft faster than Germany could shoot them down. This wasn't just about bombers. It was about showing the world what democracy, properly organized and fully committed, could achieve. It was about proving that free people, working together toward a common goal, could outproduce and ultimately defeat totalitarian regimes. It was about transforming industrial capability into strategic advantage, aluminum and rivets into hope. The assembly line at Willow Run is gone now. The workers have passed into history. The bombers they built exist mostly in museums and photographs. But the lesson remains: when civilization faces existential threats, ordinary people can accomplish extraordinary things. They just need someone to show them how. Charles Sorensen showed them how. And they built an aluminum river that helped save the world.